Unfortunately, there was some disturbance in the video, so I'm going to do this again, because in the last video, in the end of the video, I don't know what happened to the microphone. Maybe it didn't get its food, but it started acting crazy. So I'll go over this. I'll go through this again, and just to give you, for the sake of somebody who's like you didn't explain it, so I'm gonna go through this. And look, the part over here is an if and else. We already did if and else before, maybe. So I already told you that if you have an equals and equals together, that we'll have to put BNE, branch not equals. And if it was something like this, then we will put branch equals, BEQ. So here S3 is J. No, it's I, because GH is S2, S3 is I, and S4 is J. S4 is J. So understand the rest. Now I'm saying branch not equal. So if S3, which is I, and S4 is not equal, then move to else. Where is else? Else is over here. If this is instruction 1, 2, 3, 4, then you can consider that, okay, if S3 and S4 are not equal, then move to 4. And here I'm saying if I is equal to J, F equal to G plus H. Now if you think in the perspective of MIPS, I'm actually saying if I and J are not equal, then go to else. Because if I and J are equal, then I will do this. And if I and J are not equal, then I will do this. So that's exactly what is happening over here. That if I and J are not equal, then go to else. And if it is equal, then it will not go to else. It will add. Add what? S0 and S1. S0 is F, S1 is G. As you can see over here, it's clear indeed. And then you can add, oops, it's not clear indeed. Well, you have to add S1 and S2, because S1 is G and H is S2, right? And then store the result on S0, which is F. Now it's clear. And then go to exit, because this is an if and else. I don't want to continue this. If I want to continue this, then I will say something like loop, and then I'll send him to loop again, so that he can start from 1 over again. That's how you use it with loops. And I'm going to do that now. Let's see. I think I explained this in the last video, but I have to do it again because I have to remove some part because it was the terrible audio disturbance. Well, this is the offset that the I-type takes, which is in the last box if you remember, and then you have to extend it to 32 bits and do some left shifting. These 2 zeros, well, you don't have to do left shifting though, but actually you know what, I think it's better not to bring those things, because we will discuss these things later in the 3rd lecture. So let's not waste our time with that now. Let's just focus on the programming. PC is actually the program counter, which helps you go to the instruction, next instruction. So you have instruction set 1, 2, 3, 4, 5, and I told you that each instruction is 4 bytes, 32 bits, 4, 4, 4, 4, 4. So PC, what it does is it adds 4 bytes. So what 4 bits? Sorry. So which helps you. What it does is it takes you to the next, takes you to the next, takes you to the next, takes you to the next. Sequential. It does a sequential execution. 32 bits plus 4 bits, and it keeps adding. The only way you can skip this normal sequence, you already know 2, BEQ and BNQ, branch equals and branch not equals, BNE, sorry, not BNQ. If these 2 happens, these 2 have one thing at the end which can help you go to some instructions or skip some instructions. Another one is jump, J-type instructions, which will directly help you to go to, for example, if you have J5 over here, it will skip 2, 3, 4 and go to 5 directly. That's how you do this. These are, we'll discuss this. This is actually a thing of data path. And there is this J-type instruction format. J-type is one of the major thing which helps you to skip the sequential process and do some stuff. For example, in loop, we need to go back to the first sequence instruction where we started from. So that's where you need J, because PC plus 4 will keep taking you forward. but you need to repeat sometimes, you need to skip sometimes. I can't always go sequentially. I need to repeat sometimes for loops. I need to skip sometimes because there is if and else, and there's also nested if and else. So how do we do loops? That's what we're going to do now. Now this is a very important thing. I did this again. Unfortunately, I had to remove it because of the terrible audio disaster. Hope it's being recorded properly now. There are two things you need to know over here. This I'm going to spend some time over here. First is how do you deal with this, and second is how to deal with loops, which is pretty easy. This part is easy. Let's talk about this. Previously we had a scenario where we had 8, so you could easily multiply 4 to 8 and get to the value, but how are you going to multiply 4 with I? Because I is a variable. I can't just write S3 4 into 4. MIPS doesn't have anything like this. What I can do is shift left logical. Sorry, shift left logical. What it does, I told you before that it multiplies, right? So if you do SLL by 2, you're actually multiplying it by 4. So S3 is I, okay? I is S3. So I have to multiply I by 4 times. This is the same thing I did here, right? I multiplied 4 and 8. So now I will have to multiply 4 and I. So that's how you do it. SLL, left shift twice, and you get multiplication of 4. Okay, so I get 4i over here. But that's fine, I got 4i. But there could be multiple arrays. I could have saved, killed, destroyed, disappeared. There could be many arrays. How will I make MIPS understand, okay, I need to use this 4i for this? Simple. I need to add that value T1, which is actually 4i, to this address. This is exactly what we did here. For A8 we said, okay, go 4 times of T1, and this time I'm just adding instead. You see, it's very easy. S6 is the address of save. You can say A or something. Same thing. Okay, that's the case. And then how will you do while? While says if this value and this value are not equal, then stop. That's the new language I taught you in the last slide, right? If this value and this value are not equal, then stop. So that's exactly what we did here. T0 is the loaded value which I loaded. T1 is the addition of 4i to the base address S6. So this is how you get save I, okay? It will work for any arrays. And S5 is K. K is in S5. So if these two are not equal, then go to exit. Otherwise, add S3 plus 1, which is I is 1. So S3, we already did this over here. S3 plus 1. And notice that we didn't change I. I is S3. So don't think that we multiplied 4 to I. We multiplied 4 to I, but we didn't replace I. We used a temporary variable to keep the value. So I is not changed. And then this will continue until the loop is until T0 and S5 are not equal, and when they reach equality, then they will go to exit and this instruction will be skipped. Until that, instruction J will keep taking you back here. Go check until this here, again, and again, and again, and again. And this is how this loop goes on. Okay, now let's move. Okay, this is an important operation. SLT, set less than, and SLTI is same, just I type. You can say constant. So this is more like G is greater than H, and that is G is greater than 10. Constant values. So SLT can be used in if and else, and also so far we are dealing with equal and not equal. But sometimes we will need cases like less than or greater than, right? So we don't have greater than, we have SLTI, set less than. So until it is less than that, For example, I will describe this part. If S1 and S2 is less than, if S1 is less than S2, then T0 will be 1. I'm saying this again. If S1 is less than S2, then T0 will be 1. And if T0 is 1, and you check that T0 and 0 are 2 equals, then you have to exit. I need you to understand this. Let's do some tracing over here. S1 and S2. If S1 is less than S2, T0 will be 1. And now you're checking if T0 and 0 are equal. This is 0. And T0 will be 0 if they are not less than. That means if S1 is greater than S2, then T0 will be 0. And that is when you will exit the loop using L or exit, whatever. But if S1 is less than S2, as mentioned over here, then this will be 0. That means if you compare those two, this is 1 and this is 0. They are not equal. That means the loop will go on. Okay? That's how you do it. I think you'll understand better if you see it in the code. Okay. Here are some things. What you need to know about is this part. This you already know. You already know this as well. This is for storing values. This is for arguments. And this is a frame pointer. And this is a return address. Return address is for, you know, when you get return in a function. Jump and link, JAL. I'll show you the demonstration of this. And this is jump register. Return address, you remember, this is for return. Better not to talk about this and go to the direct demonstration so that you can understand. Okay, this is an interesting example. This is a function, and you have a function in Cliff example. It takes 4 arguments, 1, 2, 3, 4, 4 arguments. It has an int f, it has f, g, h, I, j, and it also has to return something. Talk about suddenly we are becoming professional. So arguments are g to j, so g, h, I, j, which are a0, a1, a2, and a3 respectively. Okay? And then you have int f. Int f is s0, so it's saved already. And result in v0. We'll store result in v0, not in temporary values. So let's see how do we deal with this. What on earth is this stack? Well, this is, let me tell you, in S0 there can be a value which is already being used. What I'm trying to say is your computer is not doing one function. It is actually involved in multiple functions. So it is very possible that at this moment the S0 I want to use has an important value of another function. So I can't just recklessly start using S0. What I will do is I will keep S0 one index ahead, and then I'll save it on index which is on the back or in the front, whatever, and then I will use S0. So what this add I does over here is SP, as you can see, SP minus 4 bits. You already know that means one, you know, one index. You're moving one index. So when you're doing that, you get the index number minus 4 bit index number, which helps you to go to the how should I put this? Previous better to show you. Suppose you have now. I'm getting a lot of distractions lately. So let me go back to what I was doing. This part is for storing the previous value in S0. Okay, we store it in a example I was writing. You have A0, A1, something like this in the stack. It's not an array. I'm just trying to show you that in the stack there is something like this, and you're putting the value of 0 in 1. You're using 0, and then when you're done with 0, you put this value back there so that it can be used again. And that's what we do over here. Look, the reverse. We stored over here, we loaded that thing from here, and then we added that thing to the +4. This is -4, that means one box ahead, and then we again added 4. This is -4, this is +4. You see? Makes sense, huh? So this is actually a process that is required for, you know, storing the value which might be required by another process. So you can say these are not part of your method. Even if you skip this, it will not stop your method. Your method part is this part. So you can kind of guess A0, A1, A2, A3. This is F plus A, G, and H plus I. Add them to two separate variables, then subtract them. And when you're done with that, store this value in a register which is used for result. Remember, we did result, the registers are V0. We can keep it here, but now we know that we will store results on V registers. So that's exactly what we did. And in the end, since there is a return, I will show you again, G plus H and I plus J, and I think you understand that part. This part, return F, you do that with JR array, this last part, segment. That's all. So that's more or less that, and now I'll show you the use of JAL, JAL. So here you can see that inside the factor, this is a recursion process. Inside we need to call this function itself. How do you do that? It's pretty simple. Ooh, is it? Yes, it is. As you can see, this 2 is again the same thing for the stack, and this time we are taking two values, and this is to restore what there was in the stack. So you basically memorize that part by understanding, of course. We start from comparing. Oh, this is for saving the arguments. You know what we get in the function. We start from SLTI. Why from SLTI? Because here is a comparison case, n is less than 1. So if n is A0, we have to use add I, because there is a constant over here, I. Okay, so let's go back. Check n is less than 1. If it is 1, then it will become, if it is less than 1, then it will become 1. And we check with this. This is the test for n is greater than 1. I think I explained this, so I'm not going to spend my time explaining it again. And this is the part where you do adding of the result, which is really simple. You just, you know, return this part. We are doing this part, n minus 1. And then we also have to do n star. So that's also later. M star will do that later. First, when the two items on the stack are popped out, the thing that we did over here, then we return the address. When will this happen? This is when you will exit the case. But if n is less than 1, that means we are supposed to enter the if, then where should we go to? L1, right? So let's go to L1. Okay, first do -1. This is n minus 1. JAL fact, call fact. Where is fact? Over here, fact. This function again, and it will go, and until BQ gives you a false result, it will keep going. This is the ending part. I'm telling you, this is the ending part. So when we return to factorial, we load the two items, and then we pop the stack, and then multiply to get the result. This part is your function actually, because this is n and this is the result, which is n minus 1, and you're calling fact for these values again. So I hope you understand that, but you will not understand until you write it. So my suggestion is write this code and then write this code along with these comments. It will be clear. Believe me, I know you're thinking it is not clear. It will be clear if you do this code and then write this one just below it. Okay, trust me, it will be. And let's see if we need to see something else. Branch addressing, I already showed you this. And no, okay, so we also need to do something a factor called float. So I'll jump to that. Let's go. MIPS, so far we were discussing about integers, but now when it comes to float, there are some complications. You see, the float, the store, and everything from integers are different for float, and float also has its own registers, okay, which is, as you can see over here, F0, F1, F2, and 32 of its own precisions with a separate CPU. So I think I should go through this at least once. Add S, single precision. If you want double precision, then I have to use add D. Same for all. Subtraction, multiplication, division, subtraction, multiplication, division. Single precision, double precision. What is single precision and double precision? To do it easily, I can just show you the difference right now. This is a single precision range, and this is a double precision range, which is bigger, obviously. Okay, you know that since you did 111. And this is a simple code for float, which is we did this just a moment ago. This is a recursion function, as you can see. We are calling fahar of oh no, we are not. This is not a recursion function, so it's easy. And this is the only code they have, which they have counted the code. So for loading float values, you have to use load C1, load C2, and dealing with them, you use these registers, not load LW, SW. Everything else is the same, except you might have noticed that the destination is these are all I types. We are using I types over here, and this is one R type instruction, and the destination there. These are two R types. No, there's three R types, and these are I types. If you want to explain this, then it is just load 1, load 2, load these two, divide them, then load fahar, which is at F12, and then you have to load this first. So load this first, F18, which is 32, and then sub it from fahar, F12, and then you store it on F18, and then multiply these two results. This is one result, this is another result. You're supposed to multiply these two because it's for this, and store it on F0. Result is in F0. Okay, so F16 this thing, F18 this thing, and then so it's the same thing. This is just an extra. Probably you will not need floating points, hopefully. So that's all for MIPS. I know I didn't cover all of the topics. There are lots of topics actually, but these are the majors, especially the parts we discussed, functions and in the beginning. Those are the real deal. So if you want to know more about MIPS, you can actually search on YouTube, and there are several videos, to be honest. And I just wanted to get you a quick review from the slides. So thank you and all the best.